welcome everybody to the HySeas string tests launch webinar. We're very pleased that you can join us today, and we will be presenting some of what we've learned over the past few months today, and we have a number of our consortium members joining us today to give you an overview of what's been happening in the HySeas project. The agenda for today is going to come out on screen very shortly. So we will start with an overview of the project from Dr. Martin Smith, who's the coordinator of the HySeas project, followed by an overview of what a string test is. Some of you have never heard about the term string test being used. So Jim Anderson will give us an overview of what a string test is. This will be followed by some videos of the launch itself. And then Kongsberg and Ballard will give us some technical details of what the string test entails and what's been happening, and how the launch of the string test went, followed by some lessons learned over the last few months and years. We will follow that with some information about what the other parts of the project have been working on, and then there'll be a Q&A session. Now, the launch of the project happened in Bergen last week, and we hoped that we had originally hoped that we could invite many of you to attend in person. However, COVID restrictions that meant that it became a primarily local affair. But we do have some pictures to show that this actually happened in practice. Yes, and so the launch day was attended by a number of people, including some VIPs and the Norwegian minister. And just as we're about to do now, there was some technical presentations, and followed by the chance to walk around and see and ask questions about what was actually going on the day. We're trying to replicate this as much as we can today, and do ask questions. When you do ask questions, please use the Q&A function and not the chat for questions to the panelists. And that will just help us to coordinate all the questions, consolidate all the questions. And if you happen to have any technical problems, then use the chat to let us know. Now, without further ado, I'm going to hand over to Martin, who will take us through an overview of the project. Martin?
Right, I'm just unmuting myself. So again, like Edwin, thanks for everyone coming along today. COVID has made things rather difficult. We haven't been able to do things in the way we had hoped to do. But of course, with this, we can actually speak to a wider range of people, and also we're recording this, and some of this will be available later. So thanks to Edwin for his description. Now, what I'm going to do is I'm going to share my screen with you. So just get that done. Right, Edwin, can everyone see this? I presume so. Right, so I have a short presentation, which is really just an introduction to what today is about, and how do we get to this place. So this is interesting. A nice picture of Stromness Harbour there. By the way, if I'm turning my head to the left a little, that's where I have the presentation shown, so I'm not being entirely rude by not looking at everyone. Oh, I just need to get that going. Right, fine, that should go. So the HySeas project team, first of all, well, who are we? There's the names of all the companies and organisations involved, and you can see there's a good spread, mostly Northern European, 3 Nordics in there, quite a few UKs, and our friends from McPhee in France and Italy mostly. But very importantly, we've got the German Aerospace Centre there, and they have done some wonderful work on environmental techno-economic modelling, some of which hopefully you will see later. So that's where we come from, that's who we are. What is HySeas III? Well, it connects 3 European partner 9 European partner organisations across 7 European countries. We are funded by the European Union's Horizon 2020 programme. Unsurprisingly, we're in line with EU's Green New Deal, Fit for 55, various other similar national, international objectives and programmes. And we're seeking to make significant progress in the elimination, not the reduction, the elimination of CO2 emissions from marine transport by developing the ability to employ green hydrogen as and fuel cell technology at commercial scale. We haven't been focusing on small boats. We want to get in about fully commercial vessels. HySeas III. Well, there must have been a HySeas II, and you're right. It's the third stage of the development programme seeking to make it possible to employ green hydrogen as a marine fuel. HySeas I was supported by Scottish Enterprise, Scottish Government, and it was a desk study some years ago examining the outline of the idea. HySeas II, well, HySeas I had told us we should look at this, so HySeas II, which was also supported by Scottish Enterprise, and we had a bit of support from the Canadian Department of Transport, was a mixture of desk study and some practical work done on the fuel cell technology itself. Could you turn it up and down? Could you roll it? The kind of conditions you find in a marine environment out at sea. So we tested a number of these things, and we developed the thinking in HySeas I to a much greater extent. I said all aspects, whether it was all aspects is subjective, but we took things to a point where it was realistic to undertake spending a lot of money on proving the concept, potentially delivering the outcome, which of course would eventually be a vessel and the supporting infrastructure. But if developing that sounds simple, I would warn people, please think again. Safety comes first and foremost with everything. I've laid out a whole lot of questions, and many of them mention safety. We need to get these things right. There can be no accidents with this sort of thing. There's crews to think about, and if there are vessels carrying passengers, that's even more regulations. So we need to think about, and regulations for very good reasons. So we need to think about all of these aspects in a lot of detail. We're going to have to transfer much larger quantities of fuel than has ever been done in hydrogen road transport. These vessels are more than an order of magnitude, even a small marine vessel, more than an order of magnitude larger than anything you're likely to find on the road. That's going to need a lot more fuel. How do you shift that and do it safely? And how do you design a vessel for safety using a quite different type of fuel? Very important questions. How big's the power system? How much space is it going to occupy? How much fuel can the vessel carry? Can we get enough fuel in there so that the vessel doesn't need to be filled up every 5 minutes? Many vessels, certainly in Scotland, are filled once a week. What training do we need for staff? What onshore safety and other procedures will be required? The list of questions is very extensive. Now, I've written another page of them, but there could have been many more. Planning and safety, marine licensing, operating regulations. What's the likely operating cost impact of this kind of change? And how will that affect local and wider society, local economies? Really important question. What are the real environmental implications as a whole? What's in the supply chain that's causing environmental impacts that perhaps you don't think about running one of these ships? We need to look at all of these things. We haven't begun to touch on the technical aspects, which today's webinar is largely about. There's nothing cheap, easy, or quick about doing this. It takes a lot of hard work. We're about 10 years into this now, some of us, and we're getting pretty close to having the answers, but it doesn't come easy. So why are we having today's webinar? Edwin's already given you some indication as to why that is. It's mainly a celebration of the project's success in completing successful construction of fully marinized, fully integrated, full-sized, modular and scalable hybrid hydrogen fuel cell lithium-ion battery, marine power system for commercial shipping. Now that's quite a mouthful. I had to think about how I was going to say that. It is a mouthful, but it explains what our objectives were. We didn't simply want to build and prove the concept of a power system which was good for one particular vessel. We wanted to be able to resize that so it can go into different sizes and types of vessels. That system, ladies and gentlemen, is now fully operational and is giving better performance than I had hoped for when we first planned this work. So this is really rather exciting. Hans and the other guys will give you details of that shortly. Also going to tell you about some other content, as Edwin mentioned. There'll be a few bits and pieces about vessel design, about fueling issues, touched on a moment ago, and also I'll come back on some of the environmental and techno-economic modelling. But I should be clear that that's the work of the German Aerospace Agency. I'm simply presenting that on behalf of them today. So that's me for now. I hope that's given you some idea of who and what we are and what we are doing. So let's hand back to Edwin, and can we move on with the show, Edwin?
Absolutely. Thank you, Martin. Yeah, and thanks for that. And so Martin mentioned the string test. And so we have Jim Anderson from Caledonian Maritime Assets Limited. I think you probably coined the term string test to tell us a little bit about what a string test is and why we're doing it. Jim?
Thanks very much, Ed. Hello, everyone. My name is Jim Anderson. I'm the Director of Vessels at Caledonian Maritime Assets Limited, based in Scotland. We currently own 37 ferries operating on various routes in the west coast of Scotland and from the Scottish mainland to the Orkney and Shetland Islands. The HySeas III project? Well, a good number of years ago, myself, along with Dr. Martin Smith from the University of St Andrews, initiated the HySeas programme, first with HySeas I and then HySeas II, and now HySeas III, which has been running for a number of years. An objective of the HySeas III programme was to carry out what we call a string test. So why carry out a string test, and what is a string test? Well, for HySeas III, the string test is to demonstrate, it's to test and verify a novel zero emissions hydrogen fueled power propulsion system for small vessels. String tests are carried out with our highly complex systems and indeed novel systems with new technologies which are untried and untested on vessels. It involves the factory functional testing of complete and entire equipment trains and their support systems, and this involves assembling all of the key powertrain components, testing them, verifying them as a complete system on the factory floor. The string test's main components included the hydrogen fuel cells, the lithium-ion battery banks, the drives, the switchboards, the hydrogen storage and the associated piping, the cooling systems and the safety systems, energy management systems, and extensive data logging. The string test is a way to mitigate risk for novel systems by fully validating the powertrain ashore. The HySeas III string test has verified that the hydrogen-fueled power systems are technically feasible. I'd like to thank everyone for all their hard work that's been involved in this HySeas programme over the years, which I understand is a world's first. So thank you very much indeed from me. Thank you.
Thank you very much, Jim. Now that we've had an introduction to the string test, we're going to show you a couple of videos from the launch of the string test last week before going into the presentations proper. So if you just bear with us, I'm going to share these videos across.
We asked ourselves a simple question. What if we looked at everything from a new perspective, a different angle, and and set our horizons towards reaching a cleaner and more sustainable future. From this new vantage point, the town of Ågotnes in Norway soared to become the center of a unique and pioneering international collaboration. Home to the world's first long-term, full-scale testing site for a groundbreaking, zero-emissions drivetrain powered by clean hydrogen fuel cells, leading the green shift towards a sustainable maritime industry. Key is our pioneering drivetrain, a device that enables motion, powered by 100 kilograms of hydrogen stored in bottles, allowing for 24 hours operation at the testing site, or, in real terms, equivalent to 15 trips by the new Orkney ferry that will carry it. Such is its industry-defining potential, the HySeas III project is funded by a European consortium, proving how hydrogen is a safe and feasible energy source for maritime use. And the process is remarkable. The fuel cells are installed in 2 containers. Inside each container, the fuel cells convert hydrogen to electric power. Batteries provided by the fuel cells provide extra power while the vessel maneuvers to and from port. Multi-drives manage and control the energy transfer from the fuel cells and batteries to propellers and main accommodation of the vessel. Switchboards connect energy sources with other areas needing to draw on them. The entire drivetrain testing is monitored and controlled from a safe and secure operations center. Here, experts monitor and gather essential information about the efficiency and performance of the drivetrain systems. Together, our team makes history.
Så skal vi til Ågotnes på Sotra, der det i dag var lansering av det som blir kallet ikke mindre enn et gjennombrott for renere skipsfart. Kongsberg-gruppen mener at de nå har teknologien for å få store skip til å gå på hydrogen. Og det kan for eksempel gjøre alle bilferger utslippsfrie.
Dette er ei bilferge. Selvsagt ikke egentlig. Men containerrekka er det som skal til for at langdistanseferger kan bli helt utslippsfrie. Sammen med en struttende stolt konserndirektør kommer en fersk næringsminister, kjempeklar til å la seg begeistre.
Jeg har gledet meg voldsomt til å komme her i dag. Ok, 1 og 2 og 3!
Knappen starter ikke støy og eksos fra dieselmotorer, men hydrogen som blir pumpet inn i brenselceller som lager elektrisitet som driver propellene.
De har kapasitet opp til 100 kW, og de kjøres best på rundt 60% av dem.
Og utslipp, ren vanndamp.
Ren vanndamp.
Dette er det grønne skiftet i praksis.
Kongsberg-gruppen og mange samarbeidspartnere lanserer det de kaller et internasjonalt gjennombrudd.
Og da sliter også konkurrentene med å kopiere oss.
Teknologien for havgående hydrogenferger er helt klar til bruk.
Det eneste du hører her nå, det er egentlig kjølekompressoren som kjører.
Vi er klar med teknologien. Dette anlegget skal antagelig installeres på Orknøyene.
Hvorfor ikke på norske ferger?
Ja, nå er det viktig at Norge også drar til. Alle bilfergene i Norge kan selvfølgelig gå med dette systemet, men de er avhengig av økonomisk støtte fra politisk hold.
Nå må vi gå gjennom hele virkemiddelapparatet vårt og se på de forutsetningene vi har for oss å få implementert teknologien i norske båter, norske fartøy, og ikke minst også koble det opp mot norske verft, sånn at vi kan bygge en grønn verdikjede i Norge og lage en verdensledende nasjon på grønn skipsfart. Ja, men det er greit. Ja, vi får gå gjennom og se. Ja, dette var stas.
Du har ikke vært statsråd så lenge, men du har lært å bli begeistret?
Ja, men jeg blir begeistret når jeg ser sånne folk som her, som satser, investerer. Og det vi har sett her er helt verdensledende, og så er det ikke science fiction langt der fremme. Det er nå det skjer.
We'll now go to Hans Westad and Christina Mikkelsen, who are project managers at Kongsberg and Ballard Power Systems, respectively, to give us a technical presentation on the string test.
My name is Hans Westad, and I am the project manager for Kongsberg Maritime for this HySeas III project. I will do a presentation of the design and construction of the string test. The objectives for work package 2 is to develop a test a full-scale drivetrain including an energy management system utilizing hydrogen and battery as the only energy source. Then we have some sub-objectives based on this objective for the work package 2. Design a complete power plant fulfilling the vessel and stakeholders' requirements. Obtain an approval of the design by the relevant certification authorities. Construct and build up the full-scale testbed, enabling the system to simulate relevant vessel operations. Establish a complete test procedure based on the concept of operation and identify hazards. Then finally, successfully accomplish test procedures and obtain the final approval for the system through the validation and test results. When we started this project, fuel cells and hydrogen was new to us in KM. We saw the need for building knowledge related to integration of hydrogen and fuel cells, as well as the control interface towards the fuel cells, and also the fuel cell dynamics. At our premises in Kongsberg, we have a flexible and powerful energy lab where we can perform development and testing of both AC and DC solutions. This energy lab was extended with hydrogen storage and fuel cell. This way, we have all subsystems for the drivetrain available at the lab, and it enables us to build knowledge related to the fuel cell dynamics and also testing all subsystems throughout the development. In the picture, you can see that outside we have one hydrogen storage container with 2 hydrogen packages of 9 kilo each. We also have a fuel cell container with 1 fuel cell of 30 kilowatt. Inside, we have a DC switchboard, or a multi-drive, as we call it, 2 battery strings, and a control room where we can control all the external equipment. We are also using a combination of motors and generators to simulate thruster load, and we have a connection to the local grid for the hotel load. During this project, we have constructed a full-scale test facility. At this test facility, we have on the outside a hydrogen storage with 2 times 50 kilogram of hydrogen. It included into this hydrogen storage is also a flow meter, enabling us to measure the amount of hydrogen we are using. There are 2 fuel cell containers with 3 fuel cells inside each, and the fuel cells are 100 kilowatt. So in total, we have 600 kilowatt of fuel cell power. We have 1 battery container with 4 battery strings. Each battery string have 180 kilowatt hours. Linked to the battery container, we have a FIFI system for the batteries. We also have 2 load banks. It's one large with 3 megawatt and one smaller with 200 kilowatt. These 2 load banks represent the thruster load in the system. Inside, we have 2 multi-drives and also a control room where we can control this system. Building a system like this for the first time, I must admit that we have had our share of challenges during the commissioning and testing. Not having a yard or vessel owner hanging over your shoulder and pushing for sheet drives gives us a much better time to do the integration and testing. in a controlled environment. In this controlled environment, we can run same sailing profiles many times with different energy management strategies. Logging the data from this test, we can optimize the usage of fuel cell and battery to maximize the efficiency and also the fuel cell lifetime. With focus on safe and working environment, we have done a lot of system safety work related to the hydrogen and fuel cells. We started with a hazard zone plan for the complete test site, and it was created together with Linde Gas as the supplier of the hydrogen storage. In general, we have only one small area with zone 1, which is the outlet of from the hydrogen storage. The other areas is zone 2. The safety hierarchy is identifying where the system can detect fire and gas. This is called the cause, and how the system shall respond to these detections. This is the effect. This safety hierarchy then makes a foundation for the cause and effect matrix that we use in our safety program. Sensor layout show where we have the installed sensors and emergency shutdown buttons. We have emergency shutdown buttons outside each of the fuel cell container and the battery container. These emergency shutdowns will shut down the containers, representative containers. We also have one emergency shutdown button inside the door where we can shut down the complete system. In the control room, we have a critical alarm and action panel. In this panel, we can see all safety alarms related to fire and gas. This is for the hydrogen storage, then we have for the fuel cell containers and for the battery. We also have emergency shutdown buttons for each of the containers where we can shut down one fuel cell or the complete container. We also have one button for a complete shutdown of the whole system. After completing the safety design, we had a design screening or a simplified hazard. This is to ensure the objectivity in the evaluation. This session was hosted by a third party. The main focus in this screening was, of course, the test site, but we also made a glance at how the design would apply to rules and regulations for a vessel. We found that the most of the identified risk was inside acceptable. 2 of the risks related to the hydrogen storage were evaluated as tolerable. And then I will hand over to Christina.
Hi, my name is Christina Mickelson, and I'm the project manager representing Ballard Power Systems in the HySeas III consortium. For this project, Ballard has purpose-built a container solution consisting of 2 20-foot shipping containers containing 6 HD7 series hydrogen fuel cells, collectively producing up to 600 kilowatts of electricity to power the drivetrain in this land-based strain test. Ballard is an industry leader in hydrogen PEM fuel cell technology. We currently run our products in buses, trains, heavy-duty trucks, and in backup power solutions. We're involved in multiple projects to bring our technology to the marine and the rail sectors. We are over 100 employees and growing in our Hobro, Denmark office, where we focus on sales, market development, engineering, manufacturing, service, support, and training. Ballard first provided Kongsberg with a single fuel cell capable of producing 30 kilowatts to facilitate learning within Kongsberg and the development of the necessary framework and expertise to integrate fuel cell technology into the energy management system that they were building at Kongsberg. Starting in December 2020, we built our container solution, completing the build and shipping them to Ågotnes in early February 2021. From their arrival on site, the containers have been installed and commissioned with the support of our technicians and technology solutions team. We have provided support both in person and virtually throughout 2021, leading up to this kickoff. With this project, Ballard fuel cells take more steps into the marine environment. We are currently finalizing the pioneering FC Wave module capable of producing 200 kilowatts of electricity. This module was built to integrate into the marine sector. This fuel cell can be used individually or as part of a larger megawatt solution and will open an exciting chapter in the decarbonization push for the shipping industry. Lessons learned. Within the HySeas III project, Ballard has learned some very valuable lessons. As we built the container solution, we learned of the need for customization and what kind of effects that can actually have on a schedule. We learned a lot about working in tight spaces, especially during a pandemic. We also learned that our decision to work with the DNVGL to go for type approval and to work with them starting earlier than we had planned was well served in achieving type approval. We learned excellent lessons regarding the shipping and delivery of hydrogen, of the glycant and glycol mix used in the cooling of the fuel cells, and even the shipping of the container themselves. We learned that redundant systems and safety go hand in hand.
Lessons learned. We have had some lessons learned during this project. The first I will address is the reverse current into the fuel cell. The fuel cell was integrated into our energy lab. To enable testing of many different configurations, we have made the energy lab very flexible. This flexibility increases the complexity of the lab, and at one point during the testing, we managed to reverse current into the fuel cell. And just to make sure, we did not produce hydrogen. We damaged the fuel cell and had to send the unit for repair. It turned out not to be damaged significantly, only a burn contactor. We saw that including a fuel cell into a large and complex system shows that the fuel cell needs to protect itself from damage, and a diode was included into the circuit to prevent reversed current. During the integration testing, we got a gas detection alarm on from the hydrogen storage container. The ESD shut down the whole system, but the leakage continued. The test team then notified the fire department and the management at the test site and at KM. The fire department again noticed the police and the ambulance as a part of their procedures. The next couple of hours was kind of hectic. This was clearly a new event for the emergency units, and a lot of questions was raised during the event. Two of the firemen went into the hydrogen container and managed to close the leakage. In a summary meeting after the incident, the fire department classified this as non-dramatic. It turned out that the leakage was due to a human error. The connection valve was not tightened properly after replacement of a package. Our team made the correct decisions, but were not certain about the decisions they made. After this incident, we have arranged a hydrogen training course to increase the knowledge in our team and updated some of the procedure related to change of hydrogen packages. Thank you.
Thank you, Hans and Christina. And actually, even though we had these incidents, particularly the hydrogen leak, it's a testament to the work that has been put in by the team looking at safety to ensure that this incident was contained and dealt with. So in some ways, it's a success story for all the safety hazard work that was carried out. Hans touched on in that last slide on safety and training. And we're going to go to David Hibbert from Technical Superintendent at Orkney Marine Services to explain a little bit about what the project and the related projects have been doing with regards to training. David?
Good morning, everyone. I'm David Hibbert from Orkney Marine Services. We are the vessel operating partner in HySeas III project. And as you can see from the slide, that illustrates the islands of Orkney. We service 13 different islands with 9 different vessels. You can see the statistics on the slide here. The main point is the vessels must be reliable and resilient, as this is the only means that the inhabitants have to have communication with the main island and then the transport back to UK mainland and further on beyond this. Yes, this slide here shows really a good illustration of the surf and turf and big hit projects, and this features on a number of locations around the islands. There's a huge number of other projects been going on out with it, which are not shown here, stretching back to the 1950s with the start of onshore wind and other land-based projects. But what I'll go over there is the projects and how they've impacted on the marine side. The Surf and Turf project was a UK-funded project to provide hydrogen for a fuel cell unit in Kirkwall Pier and cold ironing to our 3 biggest ferries for the Outer North Isles. Big Hit expanded on that with further electrolyzers on the island of Shappensea, which is of interest to HySeas III. Also the Dual Ports project, which supports us on training, that's funded by EU Interreg. Further down the line, we have Project HyDime, which is a UK-funded project, and that gave us quite a huge insight into development of onboard technology with the MV Shappensea existing ferry. And we started installing some equipment on that and developed all of the marine training. The operations manuals for the safety management system went into all of that. Project Reflex is a bigger islands-wide energy project. We're involved in the hydrogen transport. There is a combined heat and power generation station at Kirkwall Airport, not shown on this graphic. And right now we're involved with Project HyMet, which is a number of other aspects involved with the MV Shappensea, sites around Kirkwall Pier for hydrogen fuel cell and smaller mobile devices. Yes, it was noted early on in Project HyDime that the correct skill set was not available for marine crew to operate on hydrogen vessels. So we had to engage with our Maritime Coast Guard agency to see if we could get the correct skills training brought up to speed and get accreditation for that. As we know, the shipping is governed by the IMO and international regulation. We must provide crew to the STCW code and meet our operations manual through the ISM code. So quite a lot of compliance to get through on this. There's quite a bit of skills development to bring up from scratch here, and quite a lot of changes to the way we normally do things in the vessel operation. So we engaged with the University of Highlands and Islands Orkney College Marine School to start providing a training course and worked up all the modules required to get these approved with our Maritime Coast Guard agency. Sometime later, we eventually got the course approved. The certificate that you get from that is shown on the left-hand side of the slide here, and on the right-hand side is a couple of bits of the crew going through training on the assets that we have. The middle photograph is bunker training going on at the fuel cell rig. The guys are handling actually live hydrogen on that 200 bar, feeding the fuel cell unit, practicing coupling up trailers using the procedures developed for HyDime. Also in that course, there's a firefighting element which deviates from the normal training that you would get, as in you see the guys on the right-hand picture there using a thermal image camera with a hose and also breathing apparatus, looking to detect and isolate and cool rather than extinguish hydrogen. That's something that just changes everything. Very quickly to sum up here, we've gained an awful lot of operational experience over the last 5-6 years in the hydrogen space. Some illustrations in here of some of the activities we've been doing, carrying the tube trailers, operating fuel cells, getting marine projects off the ground, and which indicates that we're in a good place to move on to whatever comes next, be that in the marine space, the harbour area, or the wider Orkney context, and we look forward to that. I'll hand you over to the next presenter at this point.
Yeah, thank you very much for that, David. And if you have any questions about training, then David will be the right person to talk to, or you need to spend some time on in Orkney. Apart from training, we've also been doing a little bit of work on bunkering. And so Clara van der Kerkhove from McPhee will take us through that just now. Clara?
Hi everyone, Clara van der Kerkhove from McPhee. McPhee was the consortium member responsible for bunkering aspects, and we studied the hydrogen refueling infrastructure. You can see on the slide that the infrastructure is optimal for 2 sites, one production site and one dispensing site. The 2 of them are connected by a 30-bar pipeline. So for the production site, the idea was to produce hydrogen locally from renewables, and hydrogen production is ensured by 1 megawatt electrolyzer, which is supplied by 2 megawatt wind turbine and grid as a complement. For the dispensing site, you can see that there is 2 stations working on parallel. On the ferry side, it was decided, in order to improve resilience, that the tanks would be divided in 2 groups. So there is actually 2 stations that are needed to fuel the 2 groups in parallel. This also allows to have fueling time divided by 2. Another point is the overall cost that was estimated to be of 15 euros per kilogram of hydrogen. However, this figure should be considered carefully because it was made with very conservative hypotheses. There are 4 main conclusions to be drawn from this study. The first one is on hydrogen price, which can easily be reduced when playing on 4 criteria. So using lower electricity costs, higher utilization rate, larger scale, and fully integrated ownership of the whole energy and marine transport chain. The system considered here is the worst scenario. There is only 1 small vessel to refuel per day, and the station is in complete isolation from any other facility already existing in Orkney. So we should actually consider more integration in Orkney as a whole. Another point is replicability. So by producing a generic model, we've shown that it is replicable and feasible in other coastal areas. Feasibility was also proved. These stations are feasible nowadays with today's equipment, even if it would actually require from proper equipment developed especially for this type of application. A final point to raise is about the fueling protocol. We actually used a protocol developed by McPhee because there is no standard available nowadays for fueling large tanks. So it would require from additional validation and testing. And it also highlights the need of a standard for fueling large hydrogen tanks.
Thank you, Clara. Finally, as we draw this webinar to a close, how do we know that a hydrogen fuel cell powered ferry is the way forward from the point of view of environmental sustainability? We know that there are many different flavors and colors of hydrogen, but do we really know what the environmental impact of a fuel cell ferry would be? So Martin's got some words about that. Martin, are you ready?
Yes, I'm unmuted again. I'm just going to put my presentation thing away on it. Excellent. Right. Edwin, can you just tell me when you can see that?
I can see it.
You can see it, right. Very good. Now I seem to have lost my picture of other contributors. Whoops, I've gone down the page. Right, if anyone was wondering where I got that picture from, the action knot words are LED lights built by some of our students at the university carbon-free LED lights and carbon-free power. It's quite impressive, and a lovely drone shot from at night. It's a big theme for us, reducing CO2, right down to those that we're training to become tomorrow's technologists, economists, politicians, and yep, next generation is where we do it. Right, so what I've got here is a few slides that actually came out of a COP presentation a couple of weeks back. Not a lot in terms of slides here, but they're really important. So in the life cycle assessment that the German Aerospace Agency did for us, first thing we want to know is about carbon reduction. The numbers are pretty good. The modelling is estimating about an 80% carbon reduction. Why isn't it actually zero? Well, it is kind of zero in terms of the fuel when it's being used. But of course, there's carbon in the supply chain, in the making of the steel, the glass, the plastics, all the other bits and bobs. A great deal of the residual carbon that you're seeing there is actually in that supply chain, but it also crops up in building wind turbines and the kit you need to make and move your hydrogen around. But we wanted to know what this really looked like, and we weren't happy with just looking at some hydrogen turning into electricity. We wanted to look at the whole system. This is based on initial HySeas III's estimate inputs to the models, but from what we're seeing from the string test that we've been describing today, this is they're looking to be rather valid, and we think this is likely to be pretty close to reality. Obviously, if we want to reduce that carbon further, we have to get in about the supply chain, looking at the steel, the glass, the plastics, so on and so forth. Right, but we're not just looking at carbon. We want to understand what the other impacts are. The green, in this sort of spider web mapping, the impacts is the hydrogen fuel cell hybrid, so the type of vessel we're talking about here. And the other colours, diesel and diesel battery hybrid. In fact, if we just, I'm not going to flip back to the previous page, but you probably noticed that there isn't much difference in carbon between diesel and diesel battery. That was a surprise. It's not initially obvious, but once you start putting the whole supply chain into the model, that was a piece of learning that we didn't actually realise until it was modelled. But on this one, you can see that there are some issues with hydrogen fuel cell battery model. Around minerals and metals, carcinogenic effects, non-carcinogenic effects, freshwater ecotoxicity, and there's a bit of dissipated water down there. Those of you who are thinking about this will probably realise that's also the supply chain. This is very much about mining. It's about the way people extract cobalt, copper. There's lots of copper when you electrify, and actually these issues are common to a lot of greening. But it's important to know this, because if we don't know this, we're not looking back at our supply chain and saying, what else do we need to address? So we've done some pretty full modelling on this, right through all of the things that go into such a vessel. On the whole, I hope you can see that the green of the type of vessel we're talking about here actually occupies a lot less area than the others. There's a marked overall reduction in negative impacts on the environment. So yeah, this is good, but it's also warning us that we need to look back through our supply chains, and this is something we should never forget, because it's very easy to think we've solved one problem, but if we've created a whole lot more somewhere else. So yeah, we need to look at this, and this is something indeed that we've put quite a lot of time and effort into. This is the one that some people don't want to see. When we begin to take the information from the life cycle modelling and we start looking at the actual cost, operating cost. But I'm going to come back with something important on this. What we see, hopefully you can see my mouse, what we can see is these are our conventional vessels, whether it's a diesel electric or a diesel battery hybrid electric. And this gives us a baseline of what we know today, and this is cost. As soon as we switch to an electric basis, this is what we find. And this one here is for no-cost electricity. Simply switching from fossil to an electric basis is going to increase our costs. The other three, as you can see, these are going up. This is us parametric model, so we're just changing the expected cost of the electricity. Now, cost of electricity of about €5 per kilowatt hour. Oh, we would really like to get that at home, but with the way renewables are going, that's not unimaginable when you're buying in bulk in large quantities, or perhaps you're making it yourself. You've invested in the upfront capital rather than buying things from people. So you can imagine an integrated ownership situation, perhaps, where the whole chain is owned by the same vessel owner, operator, also producing their own electricity. Is the basis of this. So there are some things we can do, and we suspect that the eventual cost impact is probably going to be towards the smaller, down here. But it's going to cost more. Even on a free electricity basis, the lifetime cost will rise, and quite significantly. And as you can see from these simple bar charts here, the cost of green electricity, which underlies the price of green hydrogen, is by far the most significant factor in this change. There isn't a huge amount of difference in the vessel cost itself. It's a bit more expensive, but if you're amortizing that additional capital over 30, 40 years of a vessel life, it's not a terrible thing. One of the things we realized when considering fueling the vessel, and this is closely related to this type of model we're doing, it's very difficult to store very large quantities of hydrogen as a gas. We could switch over to liquid hydrogen, and indeed some people are looking at that, but as soon as you do that, you're looking at 14, 15, perhaps more % energy involved in liquefying that hydrogen. You're also looking at a plant on a vessel itself to keep the hydrogen liquid. That's weight, and there's additional capital cost for that. So quickly you sort of think, yeah, you can do this, but it's adding more to it. It's important that people do this so we get actual numbers on it. But this is part of the reasoning we've stuck to compressed hydrogen. And then when we think beyond that, what we realize is that we really need another green fuel. And the most obvious one to come from a hydrogen base actually is ammonia. Ammonia is a very relatively easy to store in liquid form, very toxic. So that's got some issues you've got to think about. But you can store very large quantities of hydrogen in effect as ammonia. And we're inclined to think that once you go for very long distance, very heavy duty vessels, that ammonia is probably the best green option. But perhaps one thing is pretty obvious. If you're going to make green ammonia, you're going to start with green hydrogen. Of course you are. There's no other way of making green ammonia. And so quite clearly, the cost of green ammonia starts with the cost of green hydrogen. So the ammonia must ultimately be more expensive. And so this is where you begin to think that you're going to end up with a two-fuel model, because you're going to use the green hydrogen where you can, simply because it's cheaper. So you can imagine that being used in and around coastal waters, and perhaps for some shorter trips. But yeah, this begins to give you some sort of insight into what the future probably is. Whilst you can burn ammonia in engines, and people are developing that now, we're expecting to see the first 2 or 3 of those appearing in the next the first of those appearing in the next 2 or 3 years. You can also put ammonia into fuel cells as well. It is relatively easy to split. So this is interesting as we look far ahead. But yeah, the cost of green ammonia is going to be higher still, and that gives us pause for thought when we consider the previous slide. Now, I said I would come back on the issue that none of us likes increasing costs. Of course we don't. But remember, when you pay more for something, that payment is going somewhere. And if that's going into your economy as well, because you're making that hydrogen, you can see that this is actually balancing out. And so this sort of thing, we can't fixate purely on cost. We've also got to think about the benefits and the benefits to the wider economy and how we capture those benefits into our economies, whether we're Norway, Denmark, France, Scotland, whatever. So we need some good policy thinking about this. And it's very important that our politicians or people that are involved in policy making are aware of some of these things. Costs will go up, but if we get this right, we should be able to capture, hopefully, lots of the benefits from this too. We can't just look at cost, we also need to look at value. And that's very, very important. I can't emphasize that highly enough. So those were just a few slides and some bits and pieces of learning from this that have really struck me personally as being very important. And I'm very pleased to be able to talk about some of these things today to a wider audience, because these are the kind of things we need to be thinking about. Long-term supply chain issues, how we manage a transition, because it's not just shipping here. The cost of many other things is going to change as we go through the transition that we're currently desperate to drive forward, and the management of that and how we capitalize on it where we can is just so important. As you can see, that's a blank page. That's me finished with the points I wanted to make today. So again, thank you for listening to us, or this part. We have more to go.
Thank you, Martin. And I hope that gave all of you a flavor of what we've been doing in the HySeas project. It's now the Q&A session, and I see some questions start to come in. I'm going to invite all the consortium members to turn on their videos so people know what you look like. And we also have, in addition to the speakers that spoke earlier on, we have with some additional panelists to answer all your difficult questions. So from Ballard, we have another Christina Julsgaard, and then from Kongsberg, we have Kette Paulsen, who's technical director at Kongsberg, and Lars Petter Nyborg, who actually has been in charge of the site and doing all the engineering and preparation there. And I think, yeah, so those are our additional panelists. We've had some questions already, both in the Q&A and in the chat. The first one, so there was an anonymous attendee who wanted to remain mysterious, who asked about in the presentation from Ballard, there was a sketch of a ferry where the fuel cell was illustrated below the waterline of the ferry. And the question was, how are the risks concerning fuel leaks mitigated in such a scenario? And I think David has some idea how we would answer that one. David.
Yeah, sorry, I actually attempted to
answer
that online, and it didn't accept the typed answer. Yeah, there is a bit of intellectual property around that. There's a thing called a tank containment space that we worked up on the HyDime project. That project's finished without conclusion, unfortunately, but all of that went through hazard consequence analysis, bow tie, risk management. Yeah, there is a bit of work to get that to approval. At the moment, the designs are, or the class society does not seem to have the appetite to take that forward, or the one that's on the new design. But we haven't stopped working on that. That's something that's a work in progress, which we'd like to keep moving. Certainly, it takes a lot of the challenges out of the amount of space that's required for storage on the vessel, if we can achieve that and operate that safely.
Martin, you've got, thanks, David. And Martin, you've got your hand up. You want to add to
that? Yes, my hand up. I would like to add to that, Edwin. I think this is something that hasn't come across particularly in the presentation, perhaps for some of those listening. And it's that there is an immense amount of regulation, both on land and at sea. And for those that are not aware of it, if you think that land-based regulation, safety regulation can be strict at times, as someone who doesn't come from a marine background, I have been amazed by the amount of regulation in the marine sector, all about safety. And as we try to do these things, it's a big organic sort of process. Lots and lots and lots of people are involved in this, and David mentioned the MCA there. That's the regulator in the UK, it's a flag state, and all of these people are having to learn about these changes as they happen. And so even if you know how to do something technically, it doesn't mean you can jump into it tomorrow and simply deliver that. The regulations don't exist for some of the things that we're doing, and it's going to take time. As I said in my opening introduction, this is not easy. It's not cheap either, but it's really important that we do this properly. Safety is at the start, the middle, and the beginning of this, and we must bring those people along with us, help them, share with them, and learn. Sorry, Edwin, I'm lecturing again.
No, that's very good. Next, we have a question from HySeas, and I think you might be able to ask your question in person if you're comfortable. So I'm just going to unmute you, HySeas, and you can ask the question directly. We'll try to make this a little bit interactive. HySeas?
Can you hear me?
Yes, very loud and clear.
Yeah, I was interested in the volumetric and the gravimetric power density comparison between the current setup and diesel or fuel oil burned in a normal engine on a ship. How do they compare?
Hi. So if you want to sort of compare with a general 200 kilowatt Cummins generator, the fuel cell is about half the weight, and the footprint is smaller, but it is taller. So in terms of just volumetric, it's a bit of a cabinet as opposed to a train car. But they'll put out about the 200 kilowatts each. But if you're comparing a fuel cell to a diesel thing, you're going to have to think about the DC to AC converter and similar, and then so there's some apples and oranges that we're working with there, but really footprint wise, it's going to be a smaller but taller item.
And is something available there? So I have to.
I'm sorry, you're cutting out quite a bit. What was that?
Documentation where this. Do you have documentation for this, or is this, let's say, sort of a back of an envelope assessment?
We're in the middle of DNV GL testing at the moment, so we do have documentation that will be ready for release in Q1.
Q1, thank you very much.
Yep.
Martin,
and
you
just to add to that,
HySeas,
you are very welcome to come visit us. We have a production line in Denmark, in Hobro right now, where the systems are being shipped out the door and to the customers for installation. So it's not a back of an envelope estimate. It's products actually leaving the factory for integration. You are very welcome to visit us if you like.
Okay. I'd be interested. Of course, COVID must help a little bit. But I'd be interested to reach out. Maybe not a physical visit, but perhaps a phone call to understand where you are. I understand the remark of back of an envelope is maybe not the right way to say it. Of course, I think there's a lot of thought behind it. But the answer that was given was maybe a ballpark answer, and so I wanted to know what was behind it. But I'm glad you are ready where you are with your production line.
And until COVID permits you to come visit us, we can provide some data specs regarding both the size, the volume, the weight, and other criteria. So drop your
Yep.
email, and Christina or me will get back to you.
Yep. Sorry, I see Christina. Yeah, thank you.
I think I'm pretty sure that Ballard's invitation extends to all the attendees and not just HySeas.
Yes, of course. Of course.
Yes, please. Just don't come all at the same time. So we can please manage that in a COVID secure manner, of course.
Martin, you wanted to add something to this?
Yeah, it's to look at the question that Keith asked in a slightly different way. This was something which, again, didn't come out during the course of the presentation at all, I think. We've been very interested since HySeas I on how far a vessel of this nature can go, what its range is. This is about storing fuel. Now, this isn't back of a bag packet calculation either, but if I can give a very simple way of looking at this, what we think is, whereas one of the 40-meter vessels that we're looking at the moment can fill with diesel and run for about a week on full tanks of diesel on their duty cycle, that we think we will get about 3 days worth on fuel tanks, 3 days worth of duty cycle. So we might have to fill twice a week or a third time on occasion. We're not entirely certain about this. It's only quite recently that we've got that plant up and running, and we need to see what fuel consumption figures eventually develop after the optimization work is finished. But hopefully that gives people some idea of what operating one of these things would look like in practice, and in terms of management, how much fuel in terms of a duty cycle can you actually get on one of these vessels if it's green hydrogen. So it looks like half the equivalent of diesel, or perhaps a little less in terms of duty cycle. So hopefully that adds a little bit to this. We should know a lot more about that in the next month or two. So hopefully that's of some help.
Thanks, Martin. On to the next question from another anonymous attendee. Are there any material, sort of steel-related degradation and design life considerations for storage and transmission of gaseous hydrogen instead of, I guess, cryogenic liquid hydrogen? Who wants to answer that one? I think just to say we're using composite tanks for this, right? Or we will be in the design.
Yeah, that's correct. They're all composite tanks of the either Type 3 or Type 4 for the hydrogen storage. With the gas pipe work has been used in the shoreside industry for decades. So there's quite a lot of information and experience to draw from in handling hydrogen out with the marine space. But, yeah, certainly there is, the hydrogen embrittlement effect that is possibly what the question is leading towards, which is a known quantity in normal carbon steels. But so the materials used in hydrogen installations are a higher specification.
Yeah.
Martin, do you wanted to add to that?
Yeah, it's an unusual one. I mean, there shouldn't be any deterioration of the hydrogen at all, really, or given the safety hazards with it, your system has to be completely sealed top to bottom. So unless you get into the sort of situation that David is describing there, and that would be a long time into the life of the hardware, as he says, the quality of fittings, pipes, etc. That you're not screwing these pipes together with a simple sort of screw fit sort of thing. They're welded. So a lot of care and attention goes into how you build these systems. There's special welding skills involved in this, and the knowledge of this comes from the refinery sector and is very well established. So I wouldn't expect there to be any issues at all, really, until you are at a point where you might see embrittlement or other long-term degradation of materials, and that may take longer than the plant life. I wouldn't expect that to be a problem.
Thanks, Martin.
Could I just add a bit to that, Edwin, if that's okay?
Sure, please.
certainly in the experience of the installations, that a design assessment is always made about minimizing number of fittings. So each fitting is always a risk of leakage. So you want to minimize the number of fittings and then look at the type of fittings that are used, which are the technology then comes from offshore oil and gas, where extreme high pressures are used. And the training is another thing about people, getting the sufficient staff to have these correct training to make these fittings. So it's not a simple means of just sticking a fitting in and screwing it up tight. There's a number of steps and a quality assurance that has to be done. So that's a skill set that has to be developed in our area.
Great, thank you, David. Next up, we've got a question in the chat from Nitin Rai. I'm going to unmute Nitin to allow him to ask the question. I think that's worked. Yes, Nitin, if you could unmute yourself, feel free to ask your question.
Yeah, thanks, Edwin. I might have just, sorry, can everyone
Yes, we can hear you loud and clear.
Yeah, great. So I might have just misread one of the graphs that was showed earlier, but it was showing, I think it showed freshwater eutrophication as a problem with the hydrogen fuel cells. Was that, I just wanted some clarification of that.
Whoops, sorry, I was muted. Yes, that is a misreading. It's not the hydrogen fuel cell in itself. This is one of the issues with mining the materials. And remember, there's also lithium-ion batteries in there, because this is an overall environmental assessment. And there's the copper and the cobalt. Mention cobalt, you start thinking of the Democratic Republic of Congo. And I guess a lot of you will have seen pictures of what lithium mining looks like. So it's all of these things. It's not directly connected to the hydrogen fuel cell, Nathan.
Great, thank you very much. Just another question. I don't know if this was answered earlier on, but it was just to do with the hydrogen consumption that you have. I wonder, was that already mentioned, or could you repeat that again? What the daily hydrogen was?
Okay. I will continue the answer to that. There was actually something shown in the slides earlier, which if you were eagle-eyed, you might have spotted it. And I am dead keen to tell people about this, so thanks for that. I'm not going to talk about actual consumption. I'm going to talk about another figure which is a bit more telling. Once the system was up and running, our amazing friends at Kongsberg discovered that we were getting 51% conversion efficiency. For those of you that know about engines, you would have a grin from one side of your face to another if you heard a figure like that. That's what I meant earlier when I said the performance was better than we expected. And that's system, that's not just the fuel cell. And also, that is before the system has been optimized. It's before we're using the batteries for peak shaving, for transients and such like. So these numbers are looking really good. But I'm a little cautious about that, and it's always wise to be cautious with these things, because we've quite a lot more testing to go yet. Eventually there will be information on this, which we'll be able to share, but the initial first look that we've had at this over the space of a few weeks, and it's been retested, and we're getting the same sort of figure, 50-51%. That's very high for an initial value. That would be a large gas turbine sort of system, or some sort of system with heat recovery, which would be much bigger than the system we're talking about here. So we can't, I wouldn't like to be definitive just yet, but this is looking pretty good. Edwin?
Oh, sorry, I was muted. Thank you for that, Martin. Here is another sort of question from an anonymous attendee. Why do we need both fuel cells and batteries? Anybody wants to answer that?
Yeah, I can give it a shot. So batteries and fuel cells together form a hybrid power solution that really extracts the best characteristics out of both technologies. The batteries are very suitable for very high power production for over a very short time, so to take out peaks in accelerating the vessel or in maneuvering. And then the fuel cells like to operate more constantly, if possible, to provide some range and some sort of a base load. And both technologies together can, in a very perfect way and efficient way, meet the energy demand and the power demand of a vessel in operation, also over longer distances. That's the point of these hybrid structures. They play very well together, and in the way they play together, they both utilize each optimal design points, and as such also secure a longer lifetime of both components in that hybrid configuration.
Thank you, Christina. I guess another question, another anonymous question. I guess this is about sizing the fuel cells. So can you run the fuel cells at maximum power for a prolonged period? Because I think the background is with engines, at least with conventional diesel engines, you tend not to want to go at 100% for too long. Is this the same for fuel cells, or is it slightly different?
You can run the fuel cell at maximum power output and also at longer times. What it does impact is the fuel consumption. So it's not the most efficient, way to utilize the fuel. The fuel cell operates most efficiently at around 40 to 70% of its maximum load, and this is where the energy efficiency is the highest. And running over a longer, over many years of service, the fuel economy and the fuel efficiency is really what drives the importance on how to best utilize your fuel cell. But there's no problem in running it at maximum load also over a longer period of time. It has no impact on, not significant impact on lifetime or other.
Thanks, Christina. Heis is back with the question. Heis, you want to ask it?
Yeah, thank you. Question was on this system efficiency, the 51% conversion efficiency. Does the team have an estimate for the conversion efficiency if peak shaving is being used using the batteries?
Edwin, do we have Lars Petter?
Yes, we do. We have Lars Petter.
He would be our man
with the data, maybe.
Yeah. Can you just please repeat the question so I try to answer it efficiently, I guess?
Yeah. Thank you.
Yeah.
So the number of 51 conversion efficiency was being quoted as system efficiency. And then the remark was made that this was conservative, as peak shaving had not yet been implemented using the batteries on board. So naturally for me, then the question pops up, what will be an estimate of the conversion efficiency if peak shaving would have been used?
Well, I can continue a little bit on that efficiency number, because this efficiency number of 51% was while we were running the vessel at its supposed range with the correct amount of load, what was designed, and the battery load and everything for the transit. So that was basically the 51% number. So it's not just running the fuel cell, it's actually running the whole vessel. And with the peak shaving is it depends on the sailing profile. For peak shaving, you want to kind of you want to eliminate the tops, right, and do the batteries. And instead of running the fuel cells on high load for a short amount of time, you want to make the batteries take the peaks. But you have to charge the batteries again. So how is the sailing profile? Is that for this vessel we are planning to charge the batteries at night, so we can run the batteries fairly low, but because we charge them at dock. But if you implement peak shaving for efficiency for the fuel, then you want to reduce the charging time again from the fuel cells. So it's it's depending on how you want to implement the peak shaving. For this vessel, we will probably, for these maneuvering modes, we will implement peak shaving so we don't run the fuel cells up and down during maneuvering. And we'll see. It's still early in the process, but that's the plan on how we're going to implement it. So hopefully that kind of answers your questions partly at least, and we'll see what the actual data shows us.
Thank you. I was interested, is there a big difference between fuel cell efficiency, vessel efficiency, system efficiency, and vessel efficiency? So the number of 51% is vessel efficiency, as I now understand.
Yeah, it's basically what theoretical kilowatt per kilograms of hydrogen and what is produced on the actual main bus. But if you include the batteries also, you can see if the batteries are charging or they are discharging, it will directly affect this kilowatt efficiency. So it's actually more of a ship performance monitoring that we need to kind of scale up for it. But for now, the initial numbers is around 51%, and we hope to increase it. But we will see during the different types of sailing profiles that we run and how it responds. We know the theory behind it, and our main goal is to kind of validate this and make it more efficient. Where do we get most bang for the buck without the big bang, of course, but just how much kilowatts can we do from actual hydrogen? So, yeah.
Yeah, thanks for that, Lars Petter. I think to sort of close off Lisa's question, we can't give you an answer to that.
Yep.
One of the things I run across sort of frequently, even just myself, is trying to actually put a kilowatt value on just to describe one of these hybrid systems. There are so many different ways you can do that. Yes, we've got 600 kilowatts of hydrogen there, but if you drained the batteries fast, you'd probably get a megawatt out of there, and Lars Petter would kill you because we'd burn the power electronics out. So how do we put a single number on that system? And it's not clear. When you then come into the fact that most sort of duty cycles, operating cycles are different for vessels, how much battery do you use? How much hydrogen do you use? And this is the question that people have been asking ever since these hybrid systems have been invented. And this is another really, really important reason as to why we have built that system, is to try the different options that Lars Petter referred to there, and use all of our best sort of thinking, not simply in modeling. We've got the system there, we can try it. We've got lots of battery there. We can try all sorts of different combinations of quantities of the two principal power elements. And as he pointed out, and it's very important, we've created the system capable of being charged from shore as well. And this question of operating cost is really important. We can buy the electricity at electricity prices. It's going to be cheaper than buying hydrogen, for the obvious reason. Hydrogen produced from electricity. So the overall equation on these things is very complicated. There's many, many different options. And this is one of the principal reasons for building this, so you can actually test it, put cost numbers into your different energy input options, and figure out what happens in the real world when you're doing this, and on different routes and duty cycles. So it's very complicated, and there is no single answer to some of these questions. A lot of it is what you want to do. What do you want that vessel to do? What are the costs of your inputs? And then figuring out how to optimize that. And this system is probably the best thing you could have if you want to answer some of those questions, along with the expertise of people like Lars Petter and Hans at Kongsberg, who specialize in this type of work. So sorry, there isn't a single answer, but we will have more numbers about this as we complete test and optimization work. I hope that helps. So it's complicated, sorry. That's me, Ed.
Gijs, were you happy with that answer, or would you like to ask something else?
Yes, no, I think I was happy with the answer. It did trigger another question, and maybe I'm claiming too much time, so I'll leave it to you to basically ask other people to come forward. But
at the moment, everyone's still a bit shy to ask questions. This is an invitation, of course, for in the last 3 or 4 minutes of this webinar for everyone else to get a question in quickly. But since your question is already up in the Q&A, we can attempt to answer it. Do you want to ask it directly?
Yeah, sure. This is not about the specific answer to the previous question, but it's if we go one level up and we combine a number of comments that were given in the presentation, different fuels, ammonia, liquid hydrogen, gaseous hydrogen, battery, electric in combination with diesel. You combine that with different ship types, ferries, but also larger vessels, larger deep sea vessels. And you look at what the joint undertaking has done in the past is they have, for some of these mobility options, like for instance for trucks and for passenger cars, they funded in the past, I would say, studies answering the question, what is the best fuel combination of fuel, powertrain, and use case in the truck sector? Has a similar study been done for the marine sector, whereby all these different stakeholder groups, engine manufacturers, fuel cell manufacturers, different types of fuel cells, different types of fuels have been tested against, let's say, what the market is at the moment actually demanding for and the market is quite diverse, from wet bulk, dry bulk, container, roll-on, roll-off, ferries, passenger ships, and so that you get a little bit more of a holistic picture of what would be applicable where, because these studies of the joint undertaking are usually a sort of a picture of 2020 and then 10 years out and 30 years out, because you actually want to decarbonize shipping, and you're looking for solutions in that space.
Thank you, Gijs. Maybe I will make a start on that one because it's the sort of in this sort of interesting policy domain. As far as I know, I'm not aware that that FCHJ has done something like this for marine, but Christina might say otherwise. I think the challenge, of course, is that certainly at the IMO level, and also at the EC level, we're still trying to agree on how we consider CO2 emissions. So do we look at it from tank to wake, or do we look at it from well to wake? And then given how the guidelines for doing those assessments are, will begin to give us an insight into how we would consider the different decarbonization options. There's the question of infrastructure. So when we look at trucks and within the FCHJ, I guess looking at land-based and in a particular geographic region, it's a bit easier, I guess, to get a head around how everything's going to work and be integrated within the EU. When you look across the world, then it becomes slightly more complicated because you need to ensure that you have sufficient quantities of relevant fuel everywhere. So, and I think in the marine industry, which you may well know, that I think we often say that there isn't really necessarily one fuel that is the front runner at this point in time. It might be a bunch of different things, but the space is very complex actually. And we need to at least get some basic foundational stuff agreed first, i.e. life cycle analysis. How are we going to do that? How do we apply that to fuels? Christina.
Yeah, I agree, Edwin. To my knowledge, also FCHJU hasn't yet made that study, but it's a very good idea to start giving some clarity around what are the opportunities, what are the maturities, and how does the industry position itself to deliver these solutions. So that point is absolutely taken. Some of the previous reports have been very beneficial. There are already some studies out there. I'd say DNV has launched a quite good study comparing the different fuels and technologies. Also, Sea Europe has worked on something along the same lines, and there's a bit of more from an academic approach, I would say, how are the opportunities here, and less industry driven. The FCHJU studies typically take an offset in what can industry deliver today in terms of solutions that match these needs, and that is still to be made. But a very good input. I can take that back into Hydrogen Europe and feed that back to FCHJU, that there are interested readers out there for such a study.
Thank you, Christine.
Would the clean hydrogen or the successor of the FCHJU be the vehicle for such a thing, or because the joint undertaking stops by the 31st of December? So what vehicle would be able to take this forward? And what role
to my
does
knowledge,
Hydrogen
it's
Europe
the Clean
still play?
Hydrogen Partnership that would take over such a role in driving it forward. The organization behind it has not changed much from FCHJU to the Clean Hydrogen Partnership. So we can expect similar activities from there. No guarantee, but that would be totally my assumption that they would pick up that something like this.
Thank you.
So we've come to the allotted time. We'll let Martin have the last word before we bid you goodbye, and happy holidays, Merry Christmas. But Martin, off you go.
I'm just checking I was unmuted. Christina said quite a lot of what I would say there, but one of the things that comes to mind, and particularly in the context of this project, is that we don't know how some of these things are going to perform yet. We don't have those ammonia engines. We don't have the complex hybrid fuel cells things that we're producing here. I think is an excellent idea. I think we absolutely have to do that. But what do we base that on? And to try and make that higher level, bigger, wider comparison. And so, hopefully what we're doing is going to feed into that, as will the people working on ammonia engines and on fuel cells, various other things. And I think it will come together. But today, there would be a lot of estimating and guesswork, I think, going into that kind of thing. I think it must come. It's really important, but we need more, as I said in the slide, action, not words, so that we've got the information that we can begin to make these decisions on, I think. So thanks, Ed.
And that's a great way to end. Well, that's a great way to end. Action, not words. And so on behalf of the consortium, thank you all for sticking with us for the last 90 minutes and listening to us. And then we wish you sort of happy holidays, Merry Christmas. There will be probably more webinars on specific topics and findings from the HySeas project next year. So keep an eye out for that. So thank you. Bye.